So we have 2.5, the derivative of trigonometric functions.
Can you turn the front light off?
Yeah.
Thanks.
2, 18, 13, 2.5. So our goal in this section is to obtain the formulas for the derivatives of the 6 basic trig functions. Sine, cosine, tangent, secant, cosecant, and cotangent. Right? I want to find the derivatives of that. So let's just start with sine. So what's the derivative of sine? Well, the only way I know to calculate derivative is by the definition, right? So the definition would be the limit as h goes to 0 of sine of x plus h minus sine of x over h. I'm going to go through the definition of the derivative of sine. Convince yourself you can follow my steps, but not that you would have pulled this out of thin air on your own. So you're not going to have to go through this derivation on your own. You're going to have to apply it once it's done, but this is kind of where it comes from. So I need to simplify this expression, and I really only have sine of h over h goes, as h goes to 0 goes to 1, and cosine of x minus 1 over h goes to 0 from the squeeze theorem, right? Those are two things I have. So I need to simplify this to get it in one of those forms to cancel them out. So if you recall, what is sine of alpha plus beta? What's another way to write that? What's the sum formula for sine? Sine of alpha, cosine of beta,
minus, what is it, cosine of alpha?
cosine of alpha, sine of beta.
Is it minus? Oh, no, it's plus.
It's plus. Okay, so maybe we couldn't pull that out of thin air, but we could at least go to our index, look it up, ask Google, get the formula, and apply it, right? So now we have this formula. We're going to apply it. X is going to play the role of alpha, and h is playing the role of beta. So to rewrite this, I have the limit as h goes to 0. So I have sine of x cosine of h plus cosine of x sine of h minus sine of x. Right? So we're not quite there yet. I would really like to see cosine of x minus 1 over x, or in this case, cosine of h minus 1 over h, because I know that goes to 0. And I also like sine of h over h, because I know that goes to 1. So I'm going to group these two terms and pull out a sine of x. Right? So I have the limit as h goes to 0. If I pull out a sine of x, I have cosine of h minus 1. So algebraically, we should be okay with that. Plus cosine of x sine of h, right? Over h. Just like one of the problems on the quiz that was like this, I can split up the h. Right? So if I do that, I have the limit as h goes to 0 of sine of x times cosine of h minus 1 over h plus cosine of x sine of h over h. Everyone agree with that? So is it 1 minus cosine of, or cosine of h minus 1 over h? 1 minus cosine of h over h. That goes to 0, right? I know the limit as h goes to 0, this goes to 0. And here, I know this goes to 1. Right? So if I apply it, I have sine times something that goes to 0, which is 0. 0 times 0 is 0. Plus, sine of x times 0 is 0. Plus cosine times 1. So here I end up with cosine of x. So that tells me that the derivative with respect to x of sine of x is cosine. So let's look at thinking about this graphically. So if I come here and I want to graph sine. So sine of x looks like this. Of course, it's periodic, so it goes on, right? And let's look at the slope at any point. What would, the slope here would be positive. It's actually positive 1. So then it's getting smaller and smaller and smaller, and it's 0. And then it's getting negative 1, and then going to 0, so forth, right? You guys can kind of see that here. The slope would be 1, 0, minus 1, 0. So here I have a slope of 0, and here I have a slope of 0. And I start up here, so I have here, minus 1, so forth. Turns out this is the graph of cosine of x. Here, this original function was sine of x. The derivative of sine is cosine. I know. I wish they'd show up too. I got, they have to have a little black in them so they show up. So maybe I'll kind of make it like this. So this is cosine. So the derivative of sine is cosine. This same can be done, the same derivation, very similar derivation with cosine. So you use the sum formula for cosine, simplify it, and it turns out the derivative of cosine is minus sine. Right? The sum formula for cosine, cosine of alpha plus cosine of beta is cosine alpha, cosine beta minus sine alpha, sine beta. So you have that negative in there. When you rearrange them, simplify, you get this negative. So let me graphically look at this formula. Might show it better. Okay, so if I graph cosine, cosine looks like this. So this is cosine. So here, my slope starts at 0, right? Pull this up a little bit. So here my slope is 0. What is my slope here? Negative. And then it goes to 0. Then it's positive 0, so forth, right? So this would be negative, at this point would be 0, so it would be negative 1, 0, positive 1, 0, so forth, right? I don't know if this one shows up any better. But if I was to graph this, this is sine flipped, right? So this turns out to be minus sine. So the derivative of cosine is minus sine. So sometimes you can just graph it real fast and remember which one's positive and which one's negative. But basically, these are the only two you have to memorize. Memorize the derivative of sine, memorize the derivative of cosine. The other 4 you can derive by the quotient rule, right? So let's look at, so we know the derivative of sine is cosine. Let's look for the derivative of cosecant. So let's say we want to find the derivative of cosecant. the derivative with respect to x of cosecant. Well, another way I can write cosecant is 1 over sine, right? So the derivative of 1 over sine using the quotient rule. The derivative of the top, hold the bottom, minus the derivative of the bottom, hold the top over the bottom squared. So if I do that, the derivative of the top is 0, right? Hold the bottom, so 0 times sine is 0. Minus, what's the derivative of sine? Cosine, right? We just learned that right here. The derivative. So I'll have 0 times sine of x minus cosine of x times 1 over sine squared. So I can rewrite this as cosine of x over, negative cosine of x over sine squared x, right?
Which rule did you use?
Quotient rule. If I have f over g prime, that's f prime g minus g prime f over g squared. Right? I know we didn't learn this too long ago, but being able to apply it here. Your book rewrites this as minus cotangent x times cosecant x. Or actually, I think they write it cosecant x, cotangent x. They're the same thing, right? You can see I can write this minus cosine x over sine of x times 1 over sine of x. So I can write that as minus cotangent cosecant or minus cosecant cotangent. I think your book uses this one. Both of them are correct. Both ways, any way you put it in Wiley, they should accept it. Yes?
Can you say say that in a sentence again, like you did something, hold something?
Here, derivative of the top, hold the bottom, minus derivative of bottom, hold the top over the bottom squared.
Okay.
There's a lot of like songs and stuff to it, like
Low D high.
yeah, low D high.
All over the square, what's below?
Okay, so you want to say that again?
Low D high minus high D low, all over the square, what's below?
There you go.
That's
So yeah, it's kind of like you remember when you learned quadratic formula, they put it to like Pop Goes the Weasel or something. Like all these fun things to remember. No one did that with you guys?
X equals negative b plus or minus square root of b squared minus 4ac all over 2a or 4
That's important in this part, but yeah, so it's all over 2a, right? But yeah, so you can have fun with it, but you need to memorize the formula because eventually you'll apply this idea to multiple quotient type problems. And eventually, if you look at the final exam, there's a whole page of just the product rule, quotient rule, chain rule with sine, cosine, polynomials, e to the x, ln of x, and all these different functions. We haven't quite got to all of them yet. We're building our toolbox of what we know the derivative of. But here, you can memorize this and say, oh, I see cosecant. I need to find the derivative of a cosecant. That's minus cosecant cotangent. I know that. Or you can say, I don't know if I remembered it correctly. I'm gonna write it out. And by doing that, I get the derivative of the quotient rule. Okay, so we have the derivative of cosecant minus cosecant cotangent. Let's see the derivative of secant.
What's the book? What are you saying?
The book summarized these for you. If you look on, let's see, the formulas from the book, the theorems from the book, chapter 2.5, they write it a little different. See if I can pull this up. 2.5.
So what the book has would be technically the final answer to it?
So here you see that the book writes it minus cosecant cotangent. It's the same to say minus cotangent cosecant. Or it would also be the same to write it like I did here, minus cosine over sine squared. If you put any of those into Wiley, it should accept it. If you do it on a quiz, I'll accept any correct answer. And the same thing with the exam.
What did you do?
Here, I wrote cosine over sine times 1 over sine. I split up the denominator of sine. So that I know cosine over sine is cotangent. And I know 1 over sine is cosecant. So I wrote it I wrote it in the way that the book shows up.
Okay.
And it turns out this one was the way the book shows up. But any of them is correct.
But isn't cosine positive there or
Here,
yeah?
well, the negative is just out front. Negative times all of this. So it's like I just want to put it out front. So
it doesn't have to be reduced, we can learn that. as a
Correct. But you might memorize it, minus cosecant, cotangent. That's a potential thing that eventually we'll apply it to multiple type problems, and you might memorize, oh yeah, derivative of cosecant, that's minus cosecant, cotangent. I just know that because I've done 500 of these problems. But if you don't, sometimes you get to final exam, and they give you secant, and you're like, crap, do I have it memorized correctly? And you want to say, okay, it takes me 2 seconds, I'll go through the derivation. Because I know sine and cosine like the back of my hand. So the derivative of secant, well, secant's 1 over cosine. So I go through the same motion. Derivative of the top is 0. Hold the bottom, doesn't matter, 0 times cosine 0. Minus, what's the derivative of cosine?
Negative sine.
Minus sine over cosine of x squared. So I can write that as sine of x over cosine times 1 over cosine. That turns out to be tangent of x times secant of x. And your book writes that secant of x times tangent of x. So the derivative of secant is secant tangent. Right? Or tangent secant. Or sine over cosine squared. A lot of times people memorize the derivative of secant and secant tangent. The derivative of cosecant is minus cosecant cotangent. So we've covered 4 of them. We have tangent and cotangent left. So let's look at the derivative of tangent. So I want to find what the derivative of tangent is. Then I need to find what the derivative of sine of x over cosine of x is. Derivative of sine? Cosine. So really I have cosine of x times cosine of x minus sine of x all over cosine of x squared. What's cosine squared plus sine squared? 1. So I can simplify this to 1 over cosine of x squared. So what's another way to write 1 over cosine? Secant. So this turns out to be secant squared x. So the derivative of tangent is secant squared.
So why was it, is it plus sign there? Is it because it was a negative sign?
Yeah. The derivative of cosine is minus sine. So minus sine is plus sine. Our last one, the derivative with respect to x of cotangent of x, which would be the derivative with respect to x. I could do 1 over tangent, since I know the derivative of tangent. Or I could do cosine over sine. Right? And we can do both ways to show you it's going to be the same answer. So the derivative of cosine minus sine of x times sine of x minus the derivative of sine, which is cosine of x times cosine of x over sine of x squared. So if I factor a negative 1 out top, I have sine squared x plus cosine squared x. So this gives me minus 1 over sine squared, which would be minus cosecant. Right?
So for here, are you doing the quotient rule and then subbing in what they equal?
Yeah. So the derivative of cosine is minus sine. Hold bottom. Minus the derivative of the bottom, the derivative of sine is cosine. Hold the top over the bottom x squared. Because I know the derivative of sine is cosine. Definitely have those 2 memorized. If you forget which one's positive, think of the graph. Or you could go through the derivation if you really wanted to.
So where do derivatives come into play, like when you're applying it? Like,
If I wanted to know the equation of the tangent line, or derivatives come into play in a lot of cases. Eventually, we're going to do application problems, and we might have a ladder leaned against a wall, and that ladder might be sliding down. And I want to know how fast is the ladder changing? How fast is it sliding down? I might want to know how fast is it moving against the wall. So this has tons of applications in engineering and physics. So I need to be able to write an equation and then differentiate it. So if you think of sine, cosine, tangent in civil engineering or physics, all over the place. So I need to find the derivative of this function. So right now it's like, okay, I'm just going through these motions. I don't really know why. Eventually we'll get application problems. Question?
You know how you said on like the first ones that if we don't reduce it down to cotangent
Mhm.
and secant, if we forget to do that,
It will be correct still.
on these two,
Mhm.
even
Yes,
though
if you
it's
leave it
more
like this on
obvious.
an exam, perfectly fine. Full points. Eventually you'll do enough of these, you'll be like, oh yeah, derivative of cotangent, that's minus cosecant squared. Derivative of tangent is secant squared. And so forth, Derivative of secant, secant tangent, derivative of cotangent, minus cosecant, cotangent. Derivative of sine, derivative of eventually you'll get there. You don't have to do this every time, right? If you're doing 30 problems, potentially, you might be really tired of doing this and just memorize it. However, I wanted to show you the derivations of each of them simply because if you get to exam, you're like, oh, am I remembering this right? Take 2 seconds and do it to convince yourself, yes, this is correct. I understand it. I remember it right, type thing. Okay, so let's look at some examples how we're going to apply this. What is the derivative of x times sine of x?
product rule and just.
Yeah, you have to remember to use a product rule. Sometimes people will say 1 times cosine x, but that's not correct. You have to use a product rule. And the product rule says the derivative of the first one, so I'm going to write this out. I take the derivative of the first function, hold the second function, plus the derivative of the second function, hold the first function. So now if I simplify this, what's the derivative of x?
1.
So I get sine of x. What's the derivative of sine? So I have cosine times x. So I write that as x times cosine. It gets a little confusing when you write your polynomial after your trig function. So if I say cosine of x times x, that might not be as clear. If you put it in Wiley correctly, it will accept it. On quizzes and exams, I just prefer this. It makes my life a little easier because I'm saying, oh, you're taking cosine of x times x. Parentheses, we'll see how it can be your friend, but this is a lot easier to see for me. So I prefer it that way.
Which way?
I prefer it this way. So this is not necessarily wrong. I just don't like seeing that. Typically, we write our polynomial before any trig functions. Any questions on that?
Sorry. The x goes to 0, right?
There's nothing going to 0. Here, this x?
Sorry. Yeah.
Yeah, this goes to 1. So typically I drop
And
it.
then,
Right, 1 times sine of x is just sine of x.
okay, so you don't find the derivative of the sine of x in the first one.
No. Right, derivative of the first function, hold the second.
And hold
Plus the derivative of the second, hold the first. Right? So this is the product rule again. But now we're applying it to trig functions and polynomials. Question?
So, when we're trying to remember these rules,
Yes.
does order matter in multiplication and not in division when you're doing?
The product rule?
Right.
Yeah, order doesn't matter because you're adding, right? Order matters in the quotient rule because you're subtracting, right? If I say 5 minus 3, that's going to be different than 3 minus 5. But if I say 5 plus 3 and 3 plus 5, there's no difference. Does that make sense?
And it's always adding unless there's something specific about the derivative that
Correct.
changes it to like plus an 8.
It
I guess I can't figure out why on tangent of x
Mm-hmm.
we added, but then cotangent of x we subtracted.
Well, because here I took the derivative of cosine, which is minus sine,
Okay.
right? So I subtracted here. Here I took the derivative of sine, which is cosine, hold the bottom, minus the derivative of cosine, which is minus sine. Minus minus is plus.
Okay.
So maybe I didn't do a too great a job
No,
of
I
explaining
understand.
that at that point, but yeah,
I knew there was a reason. I knew there was like a double negative in it.
that's where it is, because the derivative of cosine is minus sine. And that will come up. Pretty straightforward there. Okay, let's kind of just summarize, because I think it'll be kind of beneficial to see all the trig functions kind of grouped together. So the derivative of cosine, or let's write the derivative of sine first, sorry. The derivative of sine of x is cosine of x. The derivative of cosine is minus sine. The derivative of tangent is secant squared. The derivative of cosecant minus cosecant cotangent. The derivative of secant is secant tangent. And the derivative of cotangent is minus cosecant squared, sorry. Minus cosecant squared of x. Those are your book formulas for them. If you have them memorized from the book. You can derive any one of them, though, and write them differently if you prefer. So let's look at examples from Wiley. I'll let you guys finish just writing them down. Okay, so section 2, science. Just a comment, I'm going to push 2.4 back until next Monday. So, then we'll learn the quotient rule, or the chain rule, which will make one of those problems really easy to do. So 2.5. So let's look at doing these. This is one we did in the previous class.
When is the homework, or the written homework going to be due this week?
For the next kind of group, probably about 4 weeks.
3 or 4 weeks?
Yeah, probably 3 weeks. Probably 3 weeks from Friday. And that will give you time to work on 2.2, 2.3, 2.4, 2.5. Question? Would you rather turn them in every other day? No. I don't want to collect them every other day and keep track of it either, so we're on the same page. Yeah, so you should keep up with it, ideally, right? Because we'll have an exam or a quiz this Thursday, which will probably cover 2.2, 2.3, maybe 2.4. No, it'll cover 2.2 and 2.3. So ideally, you'll have those written homeworks done as we go. And then when I go to collect it, you just collect all of them, staple together, and give it to me. Ideally, right? That's not the night before you start it. That's not ideal, but probably happens more than... Okay, so let's look at the first example here. 9 cosine of x plus 7 sine of x. Do I have to use the product rule here? I don't, because these aren't... The derivative of a constant is 0. So I can just hold the constant and take the derivative of the function, right? just like we learned in 2.3, derivative of constant times the function is a constant times the derivative of the function. So what's the derivative of 9 cosine of x? Derivative of cosine minus sine, so I have 9 minus 9 sine of x. What's the derivative of 7 sine of x? 7 cosine of x. Multiple ways to write this in Wiley. You can leave it like this. You can write it as 7 cosine minus 9 sine.
But you did put the minus because of the minus sine x, right?
Yeah, so let me just kind of write this out. So I have 9 times the derivative with respect to x of cosine plus 7 times the derivative with respect to x of sine. Right? The derivative of cosine is minus sine. So yeah, I have that negative there from the derivative of cosine is minus sine. The derivative of sine is cosine, so that gets positive. Question?
And why does the 9 come out in front? Like, how is the non-effective as a derivative?
So remember from 2.3, we learned that the derivative with respect to an x of a cosine or a constant times that function is a constant times the derivative of the function.
Okay,
Good enough. The proof of the formula is in the book if you want to go back through that. But because if I take a constant times a function, the derivative is going to be the constant times the derivative of the function. You could go with the product rule here too, but the derivative of 9 is 0. Right? So you'd have 0 minus, or 0 plus negative 9 sine of x. So you could do that, but you don't have to with constants. Okay, so let's look at a few more on Wiley. This problem, so we're looking for the derivative of this function. You could expand it and deal with it, or you can just use the product rule. The derivative of the first function, hold the second one, plus the derivative of the second one, hold the first. So the derivative with respect to x of the first function, hold the second function, plus the derivative of the second function, hold the first function. Parentheses are your friend. Parentheses are my friend. When I go to grade them and you have crazy polynomials multiplied by Triggs functions and there's not a parentheses, I get very upset. So put your parentheses in there and save us both some frustration, because I will count off if you don't put your parentheses. Because technically it's wrong, right? Because if I lose the parentheses here, then it's saying this times this plus 5, not this times x squared plus 5. So those are different there. So going through here and simplifying, I get 2x times secant of x plus x squared plus 5 times, this is the derivative of secant? Secant x, tangent x. Any questions on that? If you didn't remember it, you could do it on the side and convince yourself it's secant tangent, or you could rewrite secant as 1 over cosine. So you could do the function x squared plus 5 over cosine and do the quotient rule. You're going to get the same, you're going to get a correct answer that's equivalent, but it might not look the same. So you guys remember doing trig identities in trig? The left-hand side equals the right-hand side, and you had to get there. You don't have to necessarily do that, but you could if you wanted to. That this expression you get is going to look different than this expression, but they're equivalent.
So how do we know when to stop? Because trig you can keep.
At any point you have the derivative, you can stop. I'm not asking you to get it in a certain form.
Okay.
But you could differentiate this. It's the exact same problem, but it's going to be the quotient rule, so it's going to look differently. Wiley will accept any correct answer. I will accept any correct answer on an exam or quiz. So if you do it this way, so if I want to differentiate this, the derivative of the top, hold the bottom, minus the derivative of the bottom, hold the top, over the bottom squared. These are equivalent expressions. Wiley will accept both of them. I will accept both of them. If I put this over this, they're going to end up being the same thing here. Question?
I was just gonna ask you because, like, for me, it's easier to keep them all in parentheses, like 2x is in parentheses, the secant x in parentheses.
If you want to put it like this.
Yeah, like around, even on like, yeah.
Yeah, that's perfectly fine.
I actually have the secant, those together. They're just grouped and it's like.
Oh, okay, so like just like this. That's fine. When you go to put it in Wiley, though, when you type in secant, it will give you parentheses. So, like, if I type in secant, it gives me parentheses. So that if you put parentheses on the outside, it just gets kind of busy with parentheses.
So just put
We
X
like
in there.
parentheses, but maybe not that much.
I love them.
There's a limit. But here, if you drop them here, you will lose points. You don't need any of the other ones. You just need the ones here.
So in Wiley, if you do secant of x, it'll want us to put an x in there.
Yes, definitely so. So you will put in your variable of x here.
And then just put tangent right after it.
Mm-hmm.
Yeah, but you put this here.
And it gives you the parentheses there. If you type in sine, it gives you the parentheses. If you type in cosine, so forth, it gives you the parentheses. But I wanted to show you, you can convince yourself these are the same thing, because if I find out the common denominator, cosine over cosine squared would be 1 over cosine, which is secant, which is exactly what I have here, right? And then sine over cosine would be tangent, and then 1 over cosine is secant. So I have secant tangent times x squared plus 5. And I mean, can you see here that this is maybe a little bit more confusing than x squared plus 5 times sine of x? If you put it like this, I'm not going to count it wrong. It's correct. But this is just aesthetically nicer to see, easier to grade. But if you put it in Wiley, both problems, both answers will count correct. And I will count correct. I cannot talk anymore. This is only the third time I've taught Calc 1 today. Yeah, so, yeah. Any questions on that? Multiple ways to look at it.
Just for clarity, that bottom row, that's just another way of, it's not
And-
like the next step.
No.
Okay.
This is just
Okay.
another way to look at the same problem. You might say, I love the quotient rule. I'm going to rewrite it. I only want to take derivatives of sines and cosines in my life. So I'm going to always write it as sines and cosine. If I have to do the quotient rule, I'm fine with that. And so here, I use the product rule if I want to leave it as secant. And I know the derivative of secant is secant tangent. But if I want to write it as 1 over cosine, I have to do the product rule. But I have to do the quotient rule, but I only need to know the derivative of cosine. So it's kind of a balance there. Okay. Here, like I said before, I could write this as a quotient minus a quotient, just like what we did in the notes. We took the derivative of cosecant and the derivative of cotangent. If I have them memorized, I don't have to do that. I just take, just like I did with the first example with sine and cosine, what's the derivative of cosecant?
Negative cosecant times cotangent.
Very good. So cosecant x times cotangent of x. What's the derivative of cotangent?
Negative cosine squared.
Minus cosecant squared, so I have a negative minus, so that's plus cosecant of x and all that squared. So I would use this squared. So that would be one way to write it.
Will it take it like that since? Okay, awesome.
So yeah, it will take any correct answer. What it does is it plugs it in Maple. powered by Maple. Maple is like a MATLAB computing software code, and it checks it. And it says, if I plug in, does it equal the derivative? And it does. So.
If the squared was in front of the x, like after the cosecant,
It would not. It
It
would
would
be
not.
wrong.
Okay.
Because here we're saying this cosecant is squared. If you say cosecant of x squared, you're saying square x and then take cosecant of it. But here we're saying take cosecant of x and square it.
So is that the same thing as writing the cosecant squared, then parentheses x, like how we write it on the paper?
Yes, it is. So
You just can't do that on.
you can't really do that on Wiley. Cosecant of x quantity squared, right? A lot of times we write that to emphasize that the squared's not on the x. But on
That's what it
here,
means. It's the same thing.
yeah. So if you look, when I go to input something, I can get my form. So this is saying whatever I put in the box is what's being squared. So then if I type in cosecant of x, then the square has to come up here because that's what I'm squaring. But if you put you can also hit Shift-6, which is the caret. If I put it here, this is telling me I'm squaring the x and then taking cosecant of it. Okay, this example, we're using the product rule. So the derivative of secant, whole tangent, and the derivative of tangent, whole secant. I want to get through some more, so you'll have an example of this in homework, but I want to get to a couple more. What is the derivative of this function? Try to simplify it before you differentiate it.
Sin of x times sin of x.
So if I factor out a 9, what do I have? Ooh. So what's sine squared plus cosine? What's 9 times 1? What's the derivative of 9? 0. So the derivative of this function is 0.
Oh, because you're taking out the 9 and then whatever you times that by.
It's because you're simplifying it, and this function would be a constant function of 9. If I graph this, it would be 9 all the time. And the derivative of 9 is 0. Sometimes simplifying in the beginning can make your life a little easier.
So you can do that right off the top.
You can always simplify it, yeah.
So you take out the 9.
So if I take out the 9, I'm left with sine squared x plus cosine squared x. Sine squared plus cosine is 1. So 9 times 1 is 9. And the derivative of 9 is 0. So the last, this one's pretty straightforward, just like we did in class, but x cosine x. We did x sine of x in class. This one, if I take sine of x and I differentiate it, I get cosine. If I plug in cosine at 10 pi, at 5 pi, and at pi over 4, I'll get my slope. And the last two, my last minute here, this is kind of what I was talking about of rates of change. Eventually we'll do multiple problems like this with rates of change. But here, the first thing you need to do is write an expression x equals a function of theta, and then differentiate with respect to theta. So here we end up with cosine of theta is x over 14. So x equals 14 cosine of theta. When I differentiate that and I plug in 45, it will give me my answer. And then on the bottom one, I'm using tangent, right? Tangent of theta is d over a. So I want a function of d equals a function of theta. So if I solve for that, differentiate it, and plug in 45, you'll get your answer. So we can go over these a little bit more tomorrow, but it's pretty straightforward. It doesn't give you the function, though. You have to come up with the function on your own by knowing the trig function.